Hello, Bacho, and welcome. Today, we're going to start a very important topic from our first unit, the basic properties of electric charge. Now, if you understand this properly, trust me, the rest of electrostatics becomes so much easier. We'll break it down in a very simple way so that you'll understand it perfectly and can answer any exam question without any fear.
Okay, so let's start with something you've probably all experienced. You know, in the winter, when the air is very dry, you take off a woolen sweater in a dark room, and you hear that crackling sound, and sometimes you even see tiny little sparks. So what's really happening there? Have you ever thought about it?
Well, that crackling sweater, or that small shock you sometimes get when you touch a car door handle, and even those huge dramatic lightning streaks you see in the sky, they are all connected. All these things are happening because of one single concept: electric charge.
To really get this, we first need to understand that in our entire universe, electric charge comes in only two types. Just two! This simple idea is the starting point for literally everything related to electricity.
And this brings us to what I call the golden rule of charges. It's the absolute core principle. You must remember this. The two types are called positive and negative, and how they behave is super simple. If the charges are the same, like two positives or two negatives, they will push each other away. They repel. And if the charges are different, one positive and one negative, they will pull towards each other. They attract. This attraction and repulsion is the fundamental dance of charges.
So now we know there are two types of charges, but what if you have a box with many charges inside? How do we find the total charge? Well, that brings us to the very first basic property of charge, additivity.
Now this is the exact definition from your NCERT textbook, so pay close attention. It says that the total charge of a system is simply the algebraic sum of all the individual charges present in it. That phrase, algebraic sum, is the most important part here.
But what does algebraic sum really mean? Don't worry, it's very easy. Just think of it like money in your wallet. Positive charge is like the money you have, and negative charge is like a loan you have to pay back. So to find out your total balance, what do? You just add the positives and subtract the negatives. It's nothing but the simple plus-minus maths you've been doing since school. For example, let's take the exact case from the textbook. Suppose a system has 5 charges: +1, +2, -3, +4, and -5. To find the total charge, we just add them up, remembering their signs. Cello, let's do it together. 1 + 2 gives us 3. Now 3 - 3 is 0. Then 0 + 4 is 4. And finally, 4 - 5 gives us a total charge of -1. See? It's that simple. Okay, let's move on to our second property. This one is a huge deal in physics. It's one of the great conservation laws, just like you studied about conservation of energy. This is the law of conservation of charge.
Again, this is the formal definition. It says that for an isolated system, that means a system that is not interacting with anything outside of it, the total charge inside can never ever change. You can move charge from one corner to another, but you can't just create new charge from nothing or make existing charge just disappear.
Let me give you a classic example. When you rub a glass rod with a silk cloth, the rod becomes positively charged and the silk becomes negatively charged. So, did we just create new charge? No, absolutely not. What actually happened was just a transfer. Some electrons, which are negative, literally jumped from the glass rod over to the silk cloth, so the glass rod now has fewer electrons, making it positive, and the silk has extra electrons, making it negative. The total charge of the rod and silk system is still the same as it was before we started.
Now for our third and final property. And Bacho, from an exam point of view, this one is probably the most important. It's the idea of quantization of charge. Now, the word quantization might sound a bit heavy, but the idea behind it is actually very simple.
The textbook definition says that any free charge you find in nature is always an integral multiple of a basic fundamental unit of charge, which we call E. So the total charge Q on any body can always be written as N times E, where N has to be an integer, like 1, 2, 3, or -1, -2, -3, and so on. This formula, Q equals NE, is extremely important. You must remember it.
So what does this integral multiple thing mean in simple words? It just means that charge comes in fixed packets, like coins. You can have one rupee coin, or 2 coins, or 100 coins. But you can never have 1.5 coins, right? It's the same with charge. An object can gain 1 electron, or 2 electrons, or 100 electrons, but it can never ever gain or lose 1.5 electrons. Charge always comes in these fixed chunks.
So,
what is the value of this basic packet, this fundamental unit of charge we call E? Well, it's just the charge of a single proton, which is positive E, or a single electron, which is negative E, and its value is a very, very tiny number, 1.602 into 10 to the power of minus 19 coulombs. Coulomb is just the standard unit we use to measure charge, okay?
Now, this idea of packets leads to a very common confusion point, which can be a trap in your exams. We see electricity flowing, so is charge continuous, like water flowing smoothly from a tap? Or is it made of discrete packets? What do you think?
So here's the main idea. It all depends on the scale. At the macroscopic level, in our day-to-day world, these individual packets of charge are so incredibly small, and there are so many of them, that it looks like a smooth, continuous flow. In fact, to get just 1 coulomb of charge, you need to move about 6 quintillion electrons. That's a 6 with 18 zeros after it. Can you imagine? With so many tiny packets, of course it's going to look continuous, just like a line drawn on paper looks solid from a distance. But if you could zoom in, really zoom in to the microscopic level, you would see that the line is actually made up of tiny, separate dots.
Okay, let's tackle another big silent killer. This is a mistake that students quietly make in exams and lose marks. We talked about rubbing the glass rod, right? So let me ask you again, does the act of rubbing actually create new charge from scratch? And the answer is a big, clear no. Please, remember the law of conservation. Rubbing does not create charge. It only, and I repeat, only transfers existing charge, usually electrons, from one body to another. The total charge of the whole system always remains constant. Please burn this into your memory.
All right, we've gone through the 3 basic properties. So let's quickly put everything together into a quick summary. These are the final points you absolutely need to remember for your revision and for your exams.
And why is this so important? Why are we spending so much time on this? Because, bachcho, these 3 properties, additivity, conservation, and quantization, they are the foundation of this entire chapter. Every single topic that comes after this, whether it's Coulomb's law or electric fields or potential, everything is built on these 3 fundamental rules.
So let's lock this in one last time. First, additivity. To find the total charge, just add up all the individual charges, remembering the plus and minus signs. Second, conservation. You can't create or destroy charge, you can only transfer it. And third, quantization. Charge always comes in fixed packets of size E, and the total charge is always given by the formula Q equals NE.
Let's end with a final thought. We started with that tiny little shock from a car door, right? Well, that little shock is caused by the transfer of trillions and trillions of tiny, quantized packets of charge, all happening in a flash, while the total charge of the universe is perfectly conserved. So the next time you feel that spark, you're not just getting a small shock, you are literally witnessing the fundamental laws of physics playing out right there on your fingertip. Think about that.